So Xavier is on, and this is my physics lab 2. A little bit of an introduction. The purpose of this lab is to compare our experimental projectile motion to computational models of projectile motion with and without drag. Some models and physics principles we'll be using in this lab is Newton's second law, which is over here as F net dp dt, which is most commonly known as F equals ma. And then we will also be using the velocity update formula to update our velocity in our code, and the position update formula to update our position in our code. And then we will be using the force equations for force of gravity, mg times v hat, and the v hat is just to signify direction. Same thing with the force of the drag force. It's negative b, which is a proportionality constant, times v squared, and then times again the v hat just to make it into a vector, so because there is both x and y components. And then our f net in this case, in this specific lab, is f, the force of gravity, plus the force of drag. A little bit of a preview of our results. We saw that the model with drag accurately represented the trajectory of our experiment, while the model without drag had a slightly different trajectory. Right. So as you saw in the video, our system was a white eraser, and then the surroundings were just a table in the ground. The initial conditions of our eraser were these positions you see right here in the x and y, and our initial time is not at 0 exactly, because in this video that we use in Tracker, the eraser didn't start moving until 0.566 seconds, and our initial velocity was only in the x direction since we hit it off the table horizontally, and it was 1.99 meters per second. So for our code, over here we have all the initial conditions. So the mass of our eraser was 0.02 kilograms, and then we have the initial position, initial velocity as described in the previous slide, same with the initial time and our time step, and then g, which is the acceleration of gravity, due to gravity. And then b, so when we were doing the model without drag, we just set it to 0 since we didn't have any drag, but for the model that did have drag, we had to adjust our proportionality constant until we got data that was pretty much similar to our experimental data. And for my data, we got a really small v proportionality constant of 0.00001. And then over here is the code that helps actually calculate the position and how the projectile should move in the code. So we had the magnitude of all velocity, and then we plug in the drag force equation from the beginning of the slideshow, as you see here, and then the norm Ball is the v hat, and then the force of gravity. Since the force of gravity is only in the y, we don't have to have the v hat in the code, but you could, but it's really unnecessary. And then F net equals the force of gravity plus F drag, and then we just have our velocity update formulas and our position update formula. So over here we have our models. As you can see, both the model with drag and the experimental data were both pretty close together, while the model without drag was the trajectory was slightly different. The possible sources of error, while putting the points in a Tracker, I might not put it exactly on the center of match, which could have messed with the data a little bit. And also we might have not chosen the exact right proportionality constant, but we chose the one that was close as possible, so that could have also messed with the data a little bit. So with the what does this mean question, so the model with no drag predicts the terminal velocity because it is experiencing zero net force since it is at a constant velocity, and we see that here in this top graph, and then in this bottom graph we see that the one with drag cannot accurately determine the terminal velocity. And for the what if, the time it would take to reach the ground would be pretty much the same. As you can see on the graphs, on on the left, when they both reach y equals 0, they both end up at a time that would round up to 1 second. So I made them all over here if the ball was to go straight up and straight back down. And as you can see with the values that are highlighted there, they both round up to 1 second. So it would be the same time if it was thrown directly up with the same initial velocity.